Welcome to The Explainer. All right, today we're going to tackle a topic that's, well, everywhere, from predicting elections to creating new medicines. We're talking about statistics. You can think of it as the science of making really smart calls when you just don't have all the pieces of the puzzle.
So, let's kick things off with a question that probably pops into your head every time there's an election. It just seems wild, right? How can a poll of just 1,000 people possibly tell us what millions are going to do? It feels like it shouldn't work, but the answer is, well, it's kind of brilliant, and it's all thanks to statistics.
So to crack this case, we're going to follow a roadmap. First, we'll dig into that impossible question. Then we'll get our terms straight, populations versus samples. We'll see how we bridge the gap between them, how we can estimate with confidence, and even put a claim on trial. And we'll wrap it all up with what this is really about, the science of uncertainty.
All right, let's jump right in. This is the big mystery, isn't it? How can we possibly know something about a huge group of people, millions of them, by looking at just a tiny, tiny slice?
Okay, so here's the secret sauce. It's not about asking every single person. I mean, that would be impossible, right? The real trick is finding a clever shortcut. It's about asking the right small group of people, a group that's like a perfect miniature version of the entire country.
So to really get this, we've got to get our terms right. Let's stick with our detective analogy. The population, that's the entire scene of the crime. And the sample, those are the crucial clues we find at the scene.
So you've got the population, which is the entire group we care about. For an election, that's every single eligible voter. And then you have the sample. That's the small slice we actually talked to, the 1,000 people in our poll. But here's the most important part, and I mean the absolute key. That sample has to be representative. It needs to be a mini-me of the whole population.
And here's a perfect real-world example from our source. This poll didn't survey all 46 million voters in the UK. No way. They just talked to 1,000 people. That's our sample. And looking at this breakdown, you can see how we start to get clues about the bigger picture. So you might be thinking, well, why not just ask everyone? For one thing, it's just ridiculously expensive and would take forever. But think about this. What if you're testing how long car batteries last? You can't test every single one till it dies. You wouldn't have any left to sell. Sometimes the population isn't even a real thing yet. So really, sampling is our only option. It's the only way to get the job done.
Okay, so we've got our clues from the sample, but how do we make that big leap? How do we go from those clues to saying something confident about the entire population? Well, that process has a name. It's called statistical inference, and it's basically the heart of this whole thing.
Yeah, this is where the real detective work kicks in. Inferential statistics, it's the toolbox we use to take that limited evidence from our sample and build a really solid case about the big picture. And, crucially, it also tells us just how much we can trust our own conclusions.
Inside that toolbox, we've got two main gadgets. First up is estimation. That's where we make a really educated guess about something. The second is hypothesis testing, and that's exactly what it sounds like. We put a specific claim on trial to see if it holds up.
All right, let's start with estimation. You know when you see a poll and it gives you a number, it's not just a single lonely guess. Nope. What you're actually getting is way more useful, a whole range of likely values.
So let's circle back to our UK poll. Our sample, those 1,000 people, showed 31.4% support for the Labour Party. But that's just the sample, right? The actual number for the whole country probably isn't exactly 31.4%. So what is it then?
And this is where it gets really smart. Statisticians don't just throw that 31.4% at you and call it a day. Instead, they calculate a range around it. They're basically saying, look, our best guess is that the real number for the whole population is somewhere in this ballpark. It's their way of being honest about the built-in uncertainty you get from using a sample.
This special range is called a confidence interval. And you've probably heard the phrase 95% confidence. So what does that actually mean? Well, it means that if we did this same poll 100 different times, the method we're using would give us a range that catches the true answer about 95 of those times. It's not about being 95% certain about this result, it's about being 95% confident in the method itself. Okay, tool number 2, hypothesis testing. Now we're shifting gears from just estimating to actually testing a specific claim. And honestly, the whole process feels a lot like a day in court.
So, in our little courtroom drama, you've got two opposing sides. First is the null hypothesis. Think of this as the skeptic's view, or the status quo. It basically says nothing new is happening here. Then you have the alternative hypothesis. That's the exciting new claim we're actually hoping to prove.
The weird part? We start by assuming the skeptic is right, and then we hunt for enough evidence to prove them wrong.
But here's the thing. Just like a real jury, our statistical test can make mistakes. There are two kinds. A type 1 error, that's like convicting an innocent person. We say something's going on, but really it's not. Then there's a type 2 error. That's like letting a guilty person go free. We miss something that was actually there. A huge part of statistics is managing the risk of making one of these two mistakes.
So you take all of this together, the ranges, the confidence levels, the risk of getting it wrong, and it all points to the single most important idea in statistics. It's not about finding some perfect absolute certainty.
See, statistics doesn't give us absolute certainty. What it does give us is a way to measure and talk about our uncertainty, and that's its superpower. It doesn't run from uncertainty. It puts a number on it. It quantifies it, and that is incredibly powerful.
I love this quote from one of our sources, because it just nails it. Statistics is the science of learning from data and of measuring, controlling, and communicating uncertainty. Think about that. It's the toolkit we use to push science forward, to make better decisions as a society, even when, especially when, we don't have all the answers.
So here's my challenge to you. The next time you see a poll in the news or read about a new study, don't just look at the headline number. Ask yourself, what's the uncertainty here? What's the story they're not telling me in that one single number? Because that's where you'll find the real truth of the matter.